Welcome, listeners, to the Restful Stories channel. For generations, the map of our solar system seemed complete, a family of 8 known worlds tracing their familiar paths around the sun. We are dedicated to bringing you stories from the frontiers of human knowledge. So if you'd like to be notified of our future explorations, be sure to subscribe to the channel. Beyond the orbit of the last giant, Neptune, there was thought to be only a vast and empty darkness, the cold, silent abyss that stretched between the stars. Yet, in the precise and elegant equations that described the orbits of these distant worlds, there were whispers of a ghost, a tiny, unaccounted-for wobble that suggested the gravitational tug of something else, something unseen and far away. This is the story of the hunt for that ghost. It is a tale that begins not with a sudden glimpse, but with decades of patient, meticulous searching, driven by an almost fanatical belief that our solar system had one more secret to tell. It is a story of a world that was discovered, lost its status, and in doing so, became more fascinating than its discoverers could have ever imagined. Our story is about that search, about a world found through sheer, dogged persistence. It is a story of a ghost in the darkness, a world whose existence was first whispered in the language of mathematics before it was ever captured as a flicker of light on a pane of glass. It is the story of Pluto, and it begins, as so many tales of discovery do, with a single person, staring into the silent, star-dusted dark. The story begins in the thin, cold air of northern Arizona, on a high plateau where the Lowell Observatory stands as a monument to human curiosity. It was here, on the 18th of February in the year 1930, that a young man named Clyde Tombaugh made a discovery that would redraw the map of our solar system. Tombaugh was not a formally trained astronomer with a university pedigree. He was a farm boy from Kansas, possessed of a brilliant mind, boundless patience, and a talent for building his own telescopes. Hired by the observatory just a year earlier, his task was grueling and methodical. He spent his nights exposing large glass photographic plates to the star-dusted sky, and his days hunched over a machine called a blink comparator. This device allowed him to rapidly flick between 2 images of the same star field taken on different nights. The distant stars remained fixed, but a planet, orbiting the sun, would betray its presence by moving ever so slightly against this static background. For months, Tombaugh painstakingly scanned millions of star points, a celestial needle in a cosmic haystack. Then, on that February afternoon, while examining plates taken weeks earlier in January, he saw it, a tiny speck of light that had jumped. He checked and rechecked, his heart pounding with the weight of the moment. After careful verification, the observatory announced its find to an astonished world. They had found the 9th planet. This discovery, however, was not entirely a surprise. It was the culmination of a quest that had begun decades earlier, driven by the vision, and perhaps the obsession, of the man who gave the observatory its name, Percival Lowell. A wealthy and charismatic Bostonian, Lowell had become convinced that a ninth planet, a mysterious Planet X, must exist beyond the orbit of Neptune. His conviction was rooted in mathematics, specifically in apparent discrepancies in the orbits of Uranus and Neptune. These giant planets seemed to wobble slightly in their paths, suggesting the gravitational pull of an unseen, more distant world. In 1905, Lowell initiated a systematic search program at his observatory, a search that would outlive him. He passed away in 1916, never knowing that his theoretical ghost would one day be given form and substance. The irony, discovered much later, is that the orbital discrepancies Lowell and others had calculated were based on incorrect mass estimates for Neptune. There was no gravitational wobble to explain. Planet X, as Lowell conceived it, did not exist. Clyde Tombaugh's discovery was therefore less a confirmation of a specific prediction and more a triumph of sheer, dogged persistence, a serendipitous find in the very region of the sky where Lowell had instructed his successors to look. With a new world found, a new name was needed. The tradition was to look to the Greco-Roman pantheon, the family of gods and goddesses who had lent their names to Mercury, Venus, Mars, and the other wanderers of the night sky. The name for this dark and distant object, lurking in the frigid outer reaches of the solar system, needed to evoke a sense of cold and remote gloom. The answer came not from the halls of academia, but from across the Atlantic, from the breakfast table of an 11-year-old girl in Oxford, England. Venetia Burney was a bright child, well-versed in classical mythology thanks to her grandfather, Falconer Madden, a retired librarian from the esteemed Bodleian Library at the University of Oxford. Upon reading about the discovery in the newspaper, her grandfather mentioned the challenge of naming the new planet. Venetia, without hesitation, suggested Pluto, the Roman god of the underworld, a powerful and fitting name for a world presumed to be a dark, icy realm. Her grandfather was so impressed that he immediately contacted his friend Herbert Hall Turner, a professor of astronomy at Oxford, who in turn cabled the suggestion to the astronomers at Lowell Observatory. The name was perfect. It honored the tradition. It captured the nature of the world's distant domain, and its first two letters, P and L, were the initials of Percival Lowell, a subtle and fitting tribute to the man who began the search. For the next 76 years, Pluto was cemented in human culture as the ninth planet. It was the final, lonely outpost in our solar system, a small, mysterious world about which we knew very little, but which held a firm place in our celestial family. School children memorized its name, and it became a staple of science fiction and popular imagination. But as the 20th century gave way to the 21st, our understanding of the outer solar system grew more complex. Astronomers began discovering other large, icy bodies in the same region as Pluto, a vast, remote area known as the Kuiper Belt. This growing cosmic menagerie raised difficult questions about the very definition of a planet. The tipping point came in 2005 with the discovery of Eris, an object that appeared to be even larger than Pluto. The astronomical community was faced with a choice: either add Eris and potentially dozens of other new discoveries to the official list of planets, or create a new classification that would redefine Pluto's status. In August of 2006, the International Astronomical Union, the global body responsible for astronomical nomenclature, convened in Prague and cast a historic and controversial vote. They established a new definition for a planet, and under these new rules, Pluto no longer made the cut. It was reclassified as a dwarf planet, a demotion that sparked outrage among the public and heated debate within the scientific community. Despite, or perhaps because of, this controversy, Pluto remains the most famous dwarf planet in our solar system, a celestial celebrity whose story resonates with themes of discovery, loss, and reevaluation. The debate over its status highlighted the fact that science is a dynamic and evolving process, not a static collection of facts. This reclassification also forced us to appreciate the true richness of the outer solar system. It is not an empty void with a single small planet at its edge, but a teeming, populated frontier. Pluto itself, once thought to be a solitary world, is now understood to be the king of this icy realm. For a time, it was believed that its rival, Eris, was larger. But data from the New Horizons mission in 2015 provided the first truly accurate measurements, confirming that Pluto is indeed the largest dwarf planet by diameter. It spans a remarkable 2,376 kilometers, or about 1,476 miles across. Eris, though, holds the title of the most massive, while slightly smaller in diameter at roughly 2,326 kilometers, or 1,445 miles. Its density is significantly higher, making it about 27% more massive than Pluto. This distinction between size and mass paints a more nuanced picture of these distant worlds, each with its own unique composition and history. Far from diminishing Pluto, this new context has made it even more intriguing. A complex world with its own story to tell. A story that begins with the unhurried rhythm of its rotation. A single day on Pluto, the time it takes to spin once on its axis, is an incredibly slow affair, lasting about 153 terrestrial hours, which is the equivalent of nearly 6.5 days on Earth. And if a Plutonian day seems long, its year is an almost unimaginable expanse of time. To complete a single journey around the Sun, Pluto takes 248 Earth years, a slow and majestic circuit through the deep freeze of the outer solar system. This immense orbital period puts human history into a humbling perspective. Since Clyde Tombaugh first identified it in 1930, this distant world has traversed less than a third of its path. It will not return to the same point in the sky where it was discovered until the year 2178. Generations are born, live, and die on Earth in the time it takes Pluto to complete a single season. This grand, slow waltz is not performed in a perfect circle, but in a highly eccentric or stretched ellipse. This elongated path means Pluto's distance from the Sun varies dramatically. At its closest point, known as perihelion, it swings in to about 4.4 billion kilometers, or roughly 2.8 billion miles, from our star. At its most distant, or aphelion, it retreats to a staggering 7.4 billion kilometers, or 4.6 billion miles. This orbital eccentricity produces a remarkable consequence. For a portion of its long year, Pluto's path actually brings it inside the orbit of Neptune. For 2 decades, from 1979 to 1999, Pluto was technically the 8th planet from the Sun, a temporary visitor to a neighborhood not its own. Now, having relinquished that title, it is once again on the outbound leg of its journey, slowly receding into the gloom, a process that will continue for more than a century. A celestial collision with Neptune might seem inevitable, but the two worlds are locked in a precise and stable gravitational dance called an orbital resonance. For every 3 times Neptune circles the Sun, Pluto completes exactly 2 orbits. This 3-to-2 resonance, like a perfectly timed cosmic gear, ensures they never get close enough to collide, maintaining a safe and predictable distance despite their intersecting paths. Pluto's home is not in the relatively ordered space of the major planets, but in a vast, sprawling region of icy relics known as the Kuiper Belt. This enormous donut-shaped zone begins just beyond the orbit of Neptune and extends far out into interstellar space. It is the solar system's frozen attic, a repository of countless icy bodies, the leftover building materials from the formation of the planets some 4.5 billion years ago. Its existence was first hypothesized in the mid-20th century by the Dutch-American astronomer Gerard Kuiper, who theorized that such a belt of cometary objects should lie at the edge of the solar system. For decades, it remained just a theory. But in 1992, the first Kuiper Belt object, other than Pluto, was confirmed, opening the floodgates to thousands of subsequent discoveries. We now understand this as a third distinct region of our solar system, beyond the inner rocky planets and the middle zone of the gas giants. It is a realm of profound cold and darkness, populated by dwarf planets, comets, and countless smaller icy fragments. Pluto is not a lonely outlier, but the undisputed king of this realm, the largest and most famous resident of a vast and crowded frontier. Life in this distant belt is lived under a very different sun. The light that bathes our world takes a long and lonely journey to reach Pluto. A photon leaving the fiery surface of the sun travels for 5.5 hours, crossing billions of kilometers of empty space before it finally grazes the frozen surface of the dwarf planet. By the time it arrives, its intensity is a mere ghost of its former self. The sunlight that falls on Pluto is approximately 1/900th as bright as the light we experience on a clear day on Earth. This level of illumination is comparable to the deep twilight on Earth, long after the sun has set, but before complete darkness falls. Yet, it would not be a world of absolute blackness. To a human eye, standing on Pluto's surface at high noon, the sun would appear as an intensely brilliant point of light, more like a dazzling star than the familiar disk we see in our own sky. It would still be powerful enough to cast sharp, distinct shadows, and would shine with a brightness 300 times greater than that of a full moon seen from Earth. It would be a dim, starkly lit landscape, but a landscape visible nonetheless. This remote world, once just a faint speck of light on a photographic plate, is a surprisingly small place. When we compare it to our own celestial companion, the Moon, we find that Pluto's diameter is only about 2/3 that of our satellite. It is a world dwarfed by many of the major moons in our solar system, including Jupiter's Ganymede and Saturn's Titan. Its diminutive size is even more apparent when we consider its mass. Despite being 2/3 the moon's width, it contains only about 18% of the moon's substance. This disparity reveals a fundamental difference in composition. Pluto is far less dense, a mixture of rock and a great deal of lightweight ice, rather than being a solid, rocky body like our moon. The most humbling comparison, of course, is to our own planet. Pluto is just a tiny fraction of Earth's size. Its diameter measures only about 1/5 that of our world. To put that into perspective, if you could place Pluto down upon the surface of the Earth, it would scarcely cover the continent of Australia. Its entire surface area is roughly equivalent to that of Russia. It is a small world in a vast and dark ocean, a testament to the fact that even the most seemingly insignificant objects in the cosmos can hold the most profound and fascinating secrets. Indeed, Pluto's status as a small world is firmly established when we place it in a lineup alongside the solar system's other celestial bodies. It is a world outsized by a surprising number of moons. The largest moon in our solar system, Jupiter's Ganymede, is a veritable giant in comparison, boasting a diameter so large it exceeds that of the planet Mercury. Saturn's largest moon, Titan, shrouded in its thick orange haze, is also significantly larger than Pluto. Jupiter's other Galilean moons, the volcanic and fiery Io, the ice-shelled Europa, and the heavily cratered Callisto, all surpass Pluto in sheer size. Even Neptune's largest moon, Triton, a captured Kuiper Belt object and a celestial cousin to Pluto, is slightly larger. And, of course, Earth's own moon, the familiar silver orb in our night sky, is substantially bigger and more massive. This context is crucial. For decades, Pluto was seen as the oddball planet, the small, icy runt of the litter. We now understand that it is, in fact, a perfectly normal, and indeed a very large, example of the most common type of object in the solar system, a Kuiper Belt object. It is not an undersized planet, but a king among its own kind. Beneath its exotic frozen surface, Pluto is thought to be a differentiated body, meaning its interior has settled into distinct layers. Scientists believe it harbors a large, dense core made primarily of silicate rock. This rocky heart is surrounded by a vast mantle composed of water ice. The sheer volume of this ice is staggering. Current models suggest that the water ice on Pluto, locked away in a solid, rock-hard state that forms the very bedrock of the world, is more than 3 times the total amount of water found in all of Earth's oceans combined. This is not the familiar crystalline ice of a winter's day on Earth. Under the immense pressures and cryogenic temperatures of Pluto's interior, it behaves like rock, forming the structural foundation for the mountains and plains that grace the surface. Above this deep mantle of water, ice, lies the surface we can actually observe, a delicate and complex veneer of more exotic, volatile ices. This is where the true strangeness of Pluto's chemistry comes into play. The surface is a patchwork quilt of frozen nitrogen, methane, and carbon monoxide. These are substances we know as gases on Earth, but in the profound cold of the Kuiper Belt, they behave like minerals, freezing solid to coat the landscape. Nitrogen ice, in particular, dominates vast regions, forming immense glaciers that flow and carve the surface in ways that are hauntingly familiar, yet utterly alien. The temperature on this distant world is so extreme that it defies everyday comparison. The surface of Pluto plunges to unimaginable lows, reaching between -375 and -400 degrees Fahrenheit. On the Celsius scale, this is a frigid -226 to -240 degrees. At these temperatures, the very air we breathe would freeze solid in an instant, falling to the ground as a fine, white powder. The water ice that forms Pluto's mountains is as hard and brittle as granite, while the nitrogen ice that fills its plains has the consistency of toothpaste, allowing it to flow slowly over geological timescales. This extreme cold is the driving force behind one of Pluto's most fascinating features, its tenuous and ephemeral atmosphere. Composed primarily of nitrogen gas, with trace amounts of methane and carbon monoxide, this thin atmospheric layer is not a permanent feature of the dwarf planet. Instead, it is a seasonal phenomenon, directly tied to Pluto's long, elliptical orbit around the Sun. When Pluto is closer to the Sun, as it was in the late 20th century, the faint solar warmth is just enough to cause the surface ices to sublimate, turning directly from a solid into a gas. This process creates the thin atmosphere, a delicate haze clinging to the world's surface. But as Pluto moves away from the Sun on its 248-year journey, the temperature drops even further. The atmospheric gases begin to freeze, condensing and falling back onto the surface like a gentle globe-spanning snow. For a long portion of its orbit, Pluto may have no atmosphere at all, its surface exposed directly to the vacuum of space. The atmospheric pressure on Pluto, even at its thickest, is incredibly feeble, about 100,000 times less than the air pressure we experience at sea level on Earth. This thin veil of gas is not enough to breathe, but it is enough to create weather. The New Horizons. Spacecraft detected subtle signs of winds blowing across the frozen plains, sculpting dunes and carrying haze particles to great altitudes. This haze is another surprise. High above the surface, sunlight and cosmic rays interact with the methane in the atmosphere, breaking it down and reforming it into more complex hydrocarbon molecules called tholins. These tholins, reddish-brown in color, slowly drift down and settle on the surface, contributing to Pluto's distinctive and varied coloration. They are the organic paint that colors the vast, dark regions of the world. Far from being a simple, inert ball of ice and rock, Pluto is a dynamic and geologically active world. The images sent back by the New Horizons mission in 2015 revolutionized our understanding, revealing a landscape of stunning complexity and unexpected youth. We saw towering mountains, broad, sweeping plains, deep valleys, and the scars of ancient craters. This was not a dead world, frozen in time, but a place with an ongoing geological story. The most majestic features are its mountain ranges. Some of these peaks soar to heights of between 2 and 3 kilometers, or 6,500 to 9,800 feet, rivaling the Rocky Mountains in North America. These are not mountains of rock, however. They are colossal blocks of Pluto's water-ice bedrock, pushed up from below by immense tectonic forces. This discovery was a profound shock to planetary scientists. To have mountains of this scale, there must be some internal heat source, some geological engine powerful enough to fracture and uplift the world's crust. The source of this heat remains a mystery, but its effects are undeniable, written in the very fabric of the landscape. These immense mountains of water ice, forming the very spine of Pluto's topography, are a testament to the unexpected geological forces at play. They are the rigid, unyielding bedrock of this distant world. But scattered across the surface are other features that tell a different story, one of plasticity and movement. Pluto's landscape is carved by long, deep troughs and expansive valleys, some of which stretch for 600 kilometers, or roughly 370 miles, across the frozen terrain. These are not the gentle, water-carved valleys of Earth, but vast chasms and graben, formed when the crust has been pulled apart by powerful extensional forces. It is a fractured, broken world, its surface bearing the ancient scars of interior turmoil. Among these tectonic features are the more familiar circular depressions of impact craters. Like every other body in the solar system, Pluto has endured a relentless bombardment from space over billions of years. Craters are the fossils of this violent history, each one a record of a collision with a smaller object from the Kuiper Belt. Some of these impact basins are enormous, with diameters reaching up to 260 kilometers, or 162 miles. They speak of a past when the outer solar system was a much more chaotic and crowded place. Yet, what is most striking about Pluto's craters is not their presence, but in many places, their absence. Vast stretches of the surface are smooth and nearly crater-free, a clear indication that these areas are geologically young. Some process must be actively resurfacing the dwarf planet, erasing the blemishes of ancient impacts and laying down fresh layers of ice. This was one of the most significant discoveries of the New Horizons mission, shattering the old image of Pluto as a static, frozen museum piece. We saw evidence of erosion and filling within older craters, their sharp rims softened, and their floors filled with newer, brighter ice, as if a slow, patient artist were constantly touching up the canvas of the world. This geological youth and activity are most dramatically displayed in Pluto's most famous and beloved feature, a vast, heart-shaped plain of nitrogen ice that sprawls across a significant portion of one hemisphere. The western lobe of this feature, a massive basin named Sputnik Planitia, is the vibrant, beating heart of Pluto's geology. This is not a solid, static sheet of ice. It is, in fact, an enormous glacier, a deep reservoir of frozen nitrogen that is constantly, slowly churning and flowing. This single feature, more than any other, has revealed Pluto to be a world of astonishing complexity and active processes. The story of our encounter with this dynamic world is inextricably linked to the journey of one remarkable machine. For decades, Pluto was little more than a fuzzy point of light, even to our most powerful telescopes. That all changed with the arrival of NASA's New Horizons spacecraft. Launched in 2006, the same year Pluto was reclassified, this intrepid probe embarked on a 9.5-year, 5 billion kilometer, or 3 billion mile odyssey across the solar system. It was a mission of pure exploration, a voyage to the last uncharted continent in our celestial neighborhood. On the 14th of July, 2015, New Horizons finally reached its destination, flying past Pluto and its family of moons at a blistering speed of 14 kilometers per second, or nearly 50,000 kilometers per hour. which is over 30,000 miles per hour. During its brief but historic flyby, it trained its sophisticated suite of cameras and scientific instruments on the dwarf planet, gathering a treasure trove of data that scientists will be analyzing for decades to come. Every image, every measurement revealed a world more wonderful and strange than anyone had dared to imagine. And at the center of that wonder was the great, bright heart, informally named Tombaugh Regio in honor of Pluto's discoverer. The left lobe of this heart, Sputnik Planitia, is a colossal basin filled with nitrogen ice, mixed with traces of carbon monoxide and methane. It is a landscape unlike any other in the solar system. The surface of this plane is divided into a network of irregular polygonal shapes, vast cells of ice that are typically between 10 and 40 kilometers, or 6 to 25 miles across. These shapes are the visible expression of a process known as convection. Just like a pot of simmering water on a stove or a lava lamp, the nitrogen ice at the bottom of the basin is gently warmed by Pluto's faint internal heat. As it warms, it expands, becomes less dense, and slowly rises. At the surface, it spreads out, cools, and then sinks back down along the boundaries of the cells, creating a constant, slow-motion overturning. This process, happening over thousands of years, continuously renews the surface of the plane, which is why it is completely devoid of impact craters. It is one of the youngest surfaces we have ever observed in the solar system, estimated to be less than 10 million years old, a mere blink in geological time. This discovery was profound. It meant that Pluto must have a source of internal heat, even today, billions of years after its formation. The decay of radioactive elements in its rocky core is the most likely culprit, providing just enough energy to keep this vast nitrogen glacier in a state of perpetual slow motion. This makes Pluto one of only a handful of worlds in our solar system, alongside Earth and Mars and a few icy moons, known to have actively flowing glaciers. The constant, slow churning of Sputnik Planitia is a powerful engine of geological change, but there is evidence to suggest that Pluto's surface may also be shaped by more dramatic, eruptive events. Some of the features observed by New Horizons hint at the possibility of cryovolcanism, a phenomenon where a world erupts not with molten rock, but with a frigid, slushy mixture of water, nitrogen, and methane. Scientists have identified a number of large, mountainous features with deep central depressions that bear a striking resemblance to shield volcanoes on Earth. One of these, named Right Mons, is a massive construct, about 150 kilometers or 90 miles across and 4 kilometers or 2.5 miles high. If this is indeed an ice volcano, its scale is immense, comparable to Mauna Loa in Hawaii. Instead of lava, these structures would have spewed a viscous, icy slurry that flowed across the surface before freezing solid. The source of this material would likely be a deep, subsurface layer of liquid, possibly an ancient ocean of water mixed with ammonia or other antifreeze compounds, that is kept from freezing completely by Pluto's internal heat. The idea of liquid water existing so far from the sun is tantalizing, raising profound questions about the potential for habitable environments in the darkest corners of our solar system. The flow of the nitrogen glaciers in Sputnik Planitia has created another curious and beautiful phenomenon: fleets of floating hills. Scattered across the vast, smooth plains of nitrogen ice are clusters of hills and small mountains that appear to be floating in the glacier. These are not made of nitrogen ice, but are believed to be massive chunks of the much harder, more rigid water ice that forms Pluto's underlying crust. These water ice icebergs, some of them several kilometers across, have broken away from the surrounding highlands that border the basin. They are then carried along by the slow, inexorable flow of the nitrogen ice, like wooden rafts on a river. Over millions of years, these hills are ferried from the edges of the glacier towards the centers of the convective cells, where they gather in chaotic jumbles at the points where the nitrogen ice sinks back down into the depths. This sight of mountains of water ice floating serenely on a sea of frozen nitrogen is a uniquely Plutonian landscape, a stunning illustration of how familiar materials can behave in utterly alien ways under extreme conditions of cold. Another of Pluto's unexpected and visually stunning discoveries was its white-capped mountains. High-resolution images revealed that the peaks of some mountain ranges, particularly in a dark, heavily cratered region named Cthulhu Macula, were draped in a brilliantly bright material, starkly reminiscent of snow-capped mountains on Earth. For a while, this was a deep puzzle. On Earth, mountain peaks are colder, allowing water vapor to freeze out as snow. But on Pluto, a strange temperature inversion occurs. The atmosphere is actually warmer at higher altitudes than it is on the surface. This meant that the process creating these bright caps had to be completely different from what we know on our own world. The solution to this mystery was found in Pluto's complex atmospheric cycles. The bright caps are not water snow, but methane frost. Methane is a minor component of Pluto's atmosphere, but it plays a major role in its climate. At the frigid temperatures of the Plutonian surface, methane can exist as a solid, a liquid, or a gas, much like water does on Earth. Scientists now believe that during certain points in Pluto's long seasons, methane gas becomes concentrated at high altitudes. This gas then freezes directly onto the mountain peaks, a process known as condensation, forming a fresh, bright layer of methane frost. This process is the reverse of what happens on Earth, with the snow forming where the air is warmer and richer in the condensable gas. It is a beautiful example of how the same basic physical principles can produce wildly different outcomes in different planetary environments. Pluto, the world itself, is a story of discovery and naming. But so too are its moons. The dwarf planet is the center of its own miniature solar system, a family of 5 known satellites. For nearly half a century after Pluto's discovery, it was believed to be a solitary world. That changed in 1978, when astronomer James Christie at the United States Naval Observatory in Flagstaff, Arizona, was examining photographic plates of Pluto. He noticed that the images seemed to be slightly elongated, as if Pluto had a bump on its side. By carefully analyzing older plates, he determined that this was not an imaging defect, but a large, close, orbiting moon. This moon, named Charon, after the ferrymen of the dead in Greek mythology who carried souls across the river Styx, was a revolutionary discovery. Charon is an enormous moon relative to its primary. It is fully half the diameter of Pluto and about 1/8 its mass. No other moon in the solar system is so large in comparison to its parent planet. This has led many scientists to refer to the Pluto-Charon system not as a planet and a moon, but as a binary or double dwarf planet. They are locked in a gravitational embrace so tight that they orbit a common center of mass, known as the barycenter, which lies in the empty space between them. They are also tidally locked to each other, meaning they each keep the same face perpetually turned towards the other. If you were standing on the side of Pluto that faces Charon, the great moon would hang motionless in the sky, never rising or setting, a constant and silent companion. The orbital mechanics of the Pluto-Charon system are a marvel of celestial harmony, a silent ballet performed over billions of years. But this dance is not a simple spin. Pluto's rotation is unusual among the worlds of our solar system. Like the planet Uranus, Pluto is tilted dramatically on its side. Its axis of rotation is tipped over by an angle of 120 degrees relative to its orbital plane. This extreme axial tilt means that Pluto essentially orbits the Sun lying on its side. As a result, it experiences the most extreme seasons imaginable. For decades at a time, one pole is bathed in continuous, faint sunlight, while the other is plunged into a perpetual, frigid darkness. Then, as Pluto continues its long journey, the situation slowly reverses. This severe tilt is likely another consequence of the ancient, cataclysmic impact that is thought to have formed Charon. A collision of that magnitude would have been powerful enough to knock the young Pluto completely off kilter, leaving it with the dramatic axial tilt we observe today. Another consequence of this sideways orientation is that Pluto exhibits retrograde rotation. This means it spins backward, from east to west, the opposite direction to most of the planets, including Earth. If you could stand on its surface, you would see the distant sun rise in the west and set in the east, tracing a strange and shallow arc across the sky due to the extreme tilt. This peculiar rotational behavior adds another layer of strangeness to an already alien world, a place where the fundamental rhythms of day and night are inverted. One of the key questions that the New Horizons mission sought to answer was whether Pluto possesses a magnetic field. On Earth, our powerful magnetic field is generated by the churning of a molten iron core, a process known as a dynamo. This field extends far out into space, creating a protective bubble called the magnetosphere, which shields us from the harmful solar wind. Scientists were unsure what they would find at Pluto. It was possible that its rocky core could be partially molten, or that a subsurface ocean of salty, conductive water could generate a field. However, as the spacecraft sped past, its instruments found no evidence of any intrinsic magnetic field. Pluto is magnetically inert. This means its thin atmosphere is completely exposed to the relentless stream of charged particles flowing from the sun. The solar wind is slowly but surely stripping Pluto's atmosphere away, blasting its fragile gases off into space. This process is thought to have significantly thinned the atmosphere over billions of years, and it helps to explain how material from Pluto can end up deposited on the surface of its moon, Charon. The absence of a magnetic field also means that there are no aurora on Pluto, no shimmering curtains of light to dance in its long polar nights. Another feature conspicuously absent from the Plutonian system is a set of rings. The four giant planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, all possess ring systems of varying complexity, composed of countless small particles of ice and dust. Given that Pluto has a family of small moons and is located in the debris-rich environment of the Kuiper Belt, it was plausible that it too could have a faint ring system, perhaps formed from dust kicked up by micrometeoroid impacts on its moons. The New Horizons spacecraft was specifically programmed to search for such a feature as it approached, not only for scientific interest, but also for the safety of the probe, as even a small, unseen particle could have catastrophically damaged the fast-moving spacecraft. The search turned up nothing. Pluto and its moons are a ring-free system. This absence provides important clues about the dynamics of the system, suggesting that the orbits of the small moons are stable and have not been ground down by collisions to produce the fine debris needed to form rings. Life on the surface of Pluto would be a low-gravity experience. The dwarf planet's small size and low density mean that its surface gravity is incredibly weak. It is only about 6% of Earth's gravity. A person who weighs 100 pounds on Earth would feel as light as a feather on Pluto, weighing a mere 7 pounds. You could leap to astonishing heights and bound across the frozen plains with effortless grace. This low gravity has profound implications for Pluto's geology. Mountains can rise higher before their own weight causes them to collapse, and the atmosphere, while thin, is able to extend much farther into space than it would on a higher gravity world. The scale of Pluto is often difficult to grasp, but a simple comparison can bring it into focus. If you were to take the entire surface area of the dwarf planet and lay it out flat, it would cover roughly 17.7 million square kilometers. This is a vast expanse, but it is remarkably similar to the total surface area of the country of Russia, the largest nation on Earth. It is a sobering thought that this entire, complex, and dynamic world, with its mountains, glaciers, and atmosphere, could be contained within the borders of a single terrestrial country. While it may be small in a planetary sense, Pluto is far from insignificant. When we catalog the known objects that orbit our Sun, Pluto holds a respectable position in the top 10. It is the 9th largest and 10th most massive known body that directly orbits the Sun, a list that includes all the planets and other dwarf planets like Eris and Makemake. This ranking helps to place it in its proper context, not as a failed planet, but as one of the largest and most significant members of the Sun's extended family of worlds. The New Horizons mission revealed yet another surprising aspect of Pluto, one that links it to a much different class of celestial object. As the spacecraft looked back at Pluto after its closest approach, it was able to see the faint sunlight filtering through its thin atmosphere. This revealed that the atmosphere contained layers of haze, but it also showed that Pluto has a tail, much like a comet. As the solar wind streams past Pluto, it slowly strips away nitrogen and other gases from the upper atmosphere. This material is then carried away by the solar wind, forming a long, tenuous tail of plasma that stretches out behind the dwarf planet for tens of thousands of kilometers. This discovery blurs the lines between the categories we use to classify celestial bodies. Pluto, the one-time planet, now a dwarf planet, also exhibits the behavior of a giant comet, slowly shedding its substance into the vastness of space as it journeys around the Sun. The naming of features on distant worlds is a bridge between human culture and the cosmos, a way of populating the alien landscapes with familiar stories and heroes. When the first detailed images of Pluto arrived, the scientific community was faced with a blank canvas. The Disney character, Pluto the dog, who first appeared on screen in 1930, the very same year as the dwarf planet's discovery, was famously named in its honor. The cheerful, loyal pup became an earthbound ambassador for the distant, icy world. While this connection is a charming piece of pop culture history, the official naming of Plutonian geography follows a more formal, and often more poetic, set of conventions established by the International Astronomical Union. The grand, heart-shaped feature that dominates Pluto's encounter hemisphere is a prime example. Its informal name, Tombaugh Regio, is a heartfelt tribute to Clyde Tombaugh, the tireless astronomer who first brought the world into our view. This name while widely used, has not yet been officially sanctioned. But it captures the sense of reverence and gratitude that the scientific community feels for its discoverer. One of the most unexpected discoveries within Pluto's thin atmosphere was the presence of a distinct blue sky. As the New Horizons spacecraft looked back at Pluto, with the sun eclipsed behind the dwarf planet's disk, it saw a luminous, sapphire blue ring of haze encircling the world. This was a stunning and beautiful sight, reminiscent of a sunset on Earth. The blue color is not created by the same mechanism as our own blue sky, which is caused by the scattering of sunlight by tiny nitrogen and oxygen molecules. On Pluto, the blue light is produced by the way sunlight scatters off the much larger soot-like particles of tholin in its atmospheric haze. These complex organic molecules, formed high in the atmosphere, are just the right size to scatter blue light preferentially, creating the ethereal glow that the spacecraft witnessed. It is a hauntingly familiar sight produced by entirely alien chemistry. A blue sky in a place where no life as we know it could ever breathe. The journey of the New Horizons spacecraft was itself a record-breaking feat of engineering. When it roared off its launch pad at Cape Canaveral, Florida, in January of 2006, it was propelled by the powerful thrust of an Atlas V rocket, supplemented by solid rocket boosters, and a third stage powered by a Star 48B engine. This combination of raw power gave the spacecraft the highest launch speed ever achieved by a human-made object directly leaving Earth's gravity. It screamed away from our planet at a velocity of more than 58,500 kilometers per hour, or roughly 36,400 miles per hour. At that speed, it crossed the orbit of the Moon in just 9 hours, a journey that took the Apollo astronauts 3 days. This incredible velocity was essential to get the probe to Pluto in a reasonable amount of time, but it also meant that it would arrive too fast to slow down and enter orbit. The flyby, the culmination of a decade of travel, would be over in a matter of hours. After its fleeting and triumphant encounter with Pluto, the mission of New Horizons was far from over. As it sped away, it turned its high-gain antenna back towards Earth and began the long, slow process of transmitting its priceless data home. The vast distance and the relatively low power of the spacecraft's transmitter meant that the data rate was incredibly slow, sometimes as low as 1 kilobit per second. It was like trying to stream a high-definition movie over an old dial-up modem. The complete treasure trove of images and scientific measurements, all gathered in the frantic few hours of the flyby, took more than a year to trickle back to the eager scientists on Earth. For 16 months, a steady stream of new discoveries poured in, each one painting a more detailed and revolutionary picture of the dwarf planet and its moons. While Pluto itself was the star of the show, its largest moon, Charon, proved to be a fascinating world in its own right. Discovered in 1978, Charon remained a blurry, indistinct companion for decades. The New Horizons flyby revealed it to be a world of dramatic and violent history. Its surface is a landscape of extremes, with deep canyons, towering mountains, and smooth, dark plains. A massive chasm, unofficially named Serenity Chasma, cuts across its face, a tectonic scar that is far deeper and longer than Earth's Grand Canyon. Parts of its surface are a dark, reddish-brown, particularly at its north pole, a feature nicknamed Mordor Macula. This coloration is thought to be caused by tholins, but these are not. Generated in Charon's own non-existent atmosphere. Instead, they are thought to be stolen from Pluto. Methane gas escaping from Pluto's weak gravity is captured by Charon, where it freezes onto the frigid polar regions. There, it is bombarded by solar radiation and transformed into the complex, dark red hydrocarbons that stain the surface. Charon is a world painted with the breath of its parent planet. The names given to Pluto's family of moons are all drawn from the rich tapestry of Greco-Roman mythology, specifically from figures and places associated with the underworld, in keeping with the theme of Pluto himself. Charon, the first to be discovered, is the ferryman who guides the souls of the deceased across the river Acheron. This mythological connection lends a sense of solemnity and ancient mystery to these distant, icy worlds. When the Hubble Space Telescope discovered 4 more, much smaller moons orbiting the Pluto-Charon system in the early 21st century, the naming tradition continued. Nix, discovered in 2005, is named for the Greek goddess of darkness and night, a primordial deity who was the mother of Charon. Her name is a fitting choice for a small moon orbiting in the perpetual twilight of the outer solar system. Hydra, discovered in the same year, is named for the terrifying, multi-headed serpent that guarded the entrance to the underworld in Greek mythology. This name is also a subtle nod to the New Horizons mission, as the spacecraft's initials, N and H, are Hydra's second and third letters. Kerberos, found in 2011, is named after the monstrous 3-headed dog, Cerberus in its Latin form, who stood guard at the gates of Hades. The final moon, discovered in 2012, is named Styx, for the mythological river that formed the boundary between the world of the living and the world of the dead. These names, chosen from ancient stories, imbue the Plutonian system with a sense of epic narrative, transforming these small points of light into characters in a grand cosmic drama. Pluto itself belongs to a broader category of celestial bodies known as trans-Neptunian objects, or TNOs. This is a general term for any minor planet in the solar system that orbits the Sun at a greater average distance than Neptune. The first TNO to be discovered was, of course, Pluto in 1930. For the next 6 decades, it was the only one known. Then, in 1992, the discovery of a second TNO, an object named Albion, opened the floodgates. We now know of thousands of such objects, with estimates suggesting there could be hundreds of thousands more waiting to be found. They are the frozen, pristine remnants of the early solar system, a vast population of which Pluto is the largest and most famous member. Within the vast and diverse family of trans-Neptunian objects, Pluto is also a member of a more exclusive group known as Plutoids. This is a specific subcategory created by the International Astronomical Union in 2008 to classify dwarf planets that, like Pluto, orbit the Sun beyond the path of Neptune. To be a Plutoid, a celestial body must meet the official definition of a dwarf planet, meaning it is massive enough for its own gravity to have pulled it into a nearly spherical shape, but has not cleared its orbital neighborhood of other debris, and its orbit must lie predominantly outside of Neptune's. This classification includes other prominent Kuiper Belt residents like Eris, Makemake, and Haumea. The term helps astronomers to group together these large, icy worlds of the outer solar system, distinguishing them from the only dwarf planet in the inner solar system, the asteroid belt object Ceres. The Plutoids are the royal family of the Kuiper Belt, the largest and most gravitationally dominant objects in this distant realm. One of the most tantalizing and persistent questions about Pluto is what lies hidden beneath its icy shell. The evidence of a geologically active surface, with flowing glaciers and potential ice volcanoes, strongly suggests the presence of an internal heat source. While the decay of radioactive elements in its core provides some of this heat, many scientists believe it may not be enough on its own to explain the dynamic geology we observe. This has led to the compelling hypothesis that Pluto may harbor a subsurface ocean of liquid water, buried deep beneath the thick, frozen crust of water ice, perhaps more than 100 kilometers or over 60 miles down. The pressure could be high enough, and the heat from the core just sufficient to maintain a layer of liquid. This water would likely be mixed with ammonia or other nitrogen compounds, which would act as a potent antifreeze, lowering its freezing point and making it easier to remain liquid at such cold temperatures. The existence of such an ocean would be a monumental discovery. It would place Pluto in a select group of icy worlds, including Jupiter's moon Europa and Saturn's moon Enceladus, that are considered prime candidates for hosting life beyond Earth. While the surface of Pluto is a sterile, frozen wasteland, a deep, dark ocean, warmed by geothermal vents, could potentially provide the necessary conditions: liquid water, energy, and organic molecules for life to arise and persist. The New Horizons. Data provided several clues that support the ocean hypothesis. The very existence of the Sputnik-Planitia Basin and its specific location on the globe is one of them. Such a massive basin, filled with dense nitrogen ice, represents a significant mass concentration. Over geological time, this positive mass anomaly should have caused Pluto to reorient itself, a process called true polar wander, until the basin was situated at one of its poles. However, Sputnik Planitia is located near Pluto's equator. This suggests that there is a compensating mass deficit deeper down, something that would be perfectly explained by a vast subsurface ocean, where the less dense liquid water would push up on the overlying ice crust, offsetting the heavy weight of the nitrogen glaciers above. Pluto is undeniably one of the coldest places in the entire solar system. Its great distance from the sun and its thin atmosphere, which offers little in the way of insulation, combine to create a world of extreme, perpetual cold. The surface temperatures rarely, if ever, rise above minus 223 degrees Celsius, or minus 369 degrees Fahrenheit. This cryogenic environment is the key to understanding its unique geology and chemistry. At these temperatures, water ice is as strong and unyielding as steel, forming the very foundation of the world's topography. The more volatile substances, like nitrogen, methane, and carbon monoxide, which we know as gases, are in a constant, delicate balance between their solid and gaseous states, sublimating into the atmosphere and freezing back onto the surface in a slow, grand seasonal cycle. This extreme cold has preserved the dwarf planet in a near pristine state, making it a valuable time capsule of the early outer solar system. The materials that make up Pluto are the same basic ingredients from which the giant planets and their moons were formed, but they have been kept in a deep freeze for billions of years, allowing us to study the chemistry of the primordial solar nebula. The vast, craterless plains of Sputnik Planitia provided one of the most compelling visual spectacles of the New Horizons mission, with their strange, polygonal patterns hinting at the slow convective churning of the nitrogen ice. These plains are a powerful illustration of how heat, even in minuscule amounts, can shape a landscape. The slow thermal convection that drives this process is a form of heat transfer, moving warmth from Pluto's interior towards its surface. The process is incredibly slow, with the ice rising and falling over timescales of tens of thousands of years. But its effect is profound, continuously resurfacing the plain and erasing any signs of impact craters. This makes Sputnik Planitia one of the youngest and most geologically active surfaces ever observed. This constant renewal is a powerful reminder that even in the coldest, darkest corners of the solar system, the forces of geology are still at work, shaping and reshaping worlds. The feeble gravity of Pluto has a significant and perhaps counterintuitive effect on its atmosphere. Because the gravitational pull is so weak, the atmosphere is not held tightly to the surface as it is on Earth. As a result, it is much more extended, puffing up to a far greater altitude. While the bulk of Pluto's atmosphere is concentrated within a few dozen kilometers of the surface, its outermost layers, the hazy sheath of tholins, have been detected as high as 1,600 kilometers, or 1,000 miles, above the world. This is an enormous vertical extent for such a thin atmosphere. To put it in perspective, the vast majority of Earth's atmosphere is contained within just 100 kilometers, or 62 miles, of the surface. This extended, puffy atmosphere is also more susceptible to being stripped away by the solar wind, contributing to the formation of Pluto's comet-like tail and the slow erosion of its gaseous envelope over cosmic timescales. The decision by the International Astronomical Union in 2006 to reclassify Pluto was based on a newly formalized definition of what constitutes a planet. The IAU established 3 specific criteria that a celestial body must meet to be granted full planetary status. First, it must be in orbit around the Sun. Second, it must have sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, or nearly round shape. Third, it must have cleared the neighborhood around its orbit, meaning it has become the gravitationally dominant object in its orbital zone, sweeping up or flinging away most other smaller objects. Pluto successfully meets the first 2 of these criteria. It orbits the Sun, and it is large enough to be spherical. However, it fails on the third count. Its orbit is situated in the heart of the Kuiper Belt, a crowded region filled with thousands of other icy bodies. Pluto has not cleared its neighborhood. It is a part of it. This third criterion was the specific reason for its demotion to the status of dwarf planet, a decision that remains a subject of passionate debate among scientists and the public alike. The discovery of a growing number of other large objects in the Kuiper Belt throughout the late 1990s and early 2000s was the primary catalyst for this reevaluation. Objects like Quaoar, Sedna, and especially Eris, which was initially thought to be larger than Pluto, presented a direct challenge to the traditional 9-planet model of the solar system. Astronomers realized they were on the verge of opening a celestial Pandora's box. If Pluto was a planet, then Eris surely had to be one as well. And if Eris was a planet, then what about the dozens of other large spherical objects that were likely to be discovered as survey technology improved? The solar system might soon have 50 planets or more. The reclassification was, in many ways, a pragmatic response to this new and more complex understanding of the outer solar system. It was an attempt to draw a scientifically meaningful line, to create a classification system that reflected the reality of a solar system that was far more crowded and diverse than previously thought. The home of the institution that started it all, the Lowell Observatory, is perched on a hill overlooking the city of Flagstaff, Arizona. It was here that Percival Lowell built his astronomical legacy, and it was from here that Clyde Tombaugh peered into the void, and found a new world. The observatory remains a world-class research facility, but it is also a historical landmark, a place of pilgrimage for those fascinated by the story of Pluto. The 1930 discovery of the ninth planet remains the observatory's most famous achievement, a moment that forever linked the clear, dark skies of northern Arizona with the faint, frozen plains of a world billions of miles away. The great heart of Pluto, the sprawling and brilliant Tombaugh Regio, is a feature of continental scale. It stretches more than 1,600 kilometers, or 1,000 miles, across the surface, a vast expanse of bright, reflective ice. It is the dominant feature of the hemisphere that faced the New Horizons spacecraft during its closest approach, and it has become the iconic symbol of the new, dynamic Pluto. This single, massive feature, a combination of a vast nitrogen glacier and adjacent highlands coated in bright frost, tells a story of complex geology, seasonal cycles, and a surprisingly active interior. It is the bright, enigmatic smile of a world that had, for so long, kept its secrets hidden in the dark. The intimate gravitational relationship between Pluto and Charon results in a fascinating exchange of materials, a one-way traffic of atmospheric gases. The reddish-brown cap that stains Charon's North Pole is a direct and visible consequence of this celestial sharing. This distinctive coloration is caused by tholins, the same complex organic molecules found on Pluto's surface. However, Charon itself is too small and has too little gravity to maintain its own atmosphere, so it cannot produce these tholins locally. Instead, the raw materials are gifted from Pluto. The methane gas that escapes from the top of Pluto's extended atmosphere is captured by Charon's weak gravitational pull as it orbits through the tenuous outer fringes of this gaseous halo. This captured methane then migrates to the coldest parts of Charon's surface, its poles, which experience a winter darkness that lasts for more than a century. During this long, deep freeze, the methane condenses onto the surface as ice. Once there, it is exposed to the faint but persistent ultraviolet light from the sun. This radiation triggers a chemical reaction, a process called photolysis, which breaks the methane molecules apart and allows them to recombine into the larger, more complex tholin molecules. These tholins have a naturally reddish hue and are much less volatile than the methane ice they formed from, so they remain on the surface even when the long winter finally ends and the pole returns to sunlight. Over billions of years, this gentle, persistent snowfall of borrowed gas has built up a significant, dark, red deposit, painting Charon's pole with the chemical signature of its parent world. This process makes Charon a unique kind of cosmic archivist, collecting and preserving a sample of Pluto's atmospheric history on its own frozen surface. The internal structure of Pluto inferred from its density and gravitational pull, points to a world that has undergone differentiation, the process by which a planetary body settles into distinct layers of varying density. Early in its history, shortly after its formation from the accretion of smaller icy and rocky planetesimals, Pluto would have been a more uniform mixture of these materials. However, the heat from the impacts of its formation, combined with the energy released by the decay of radioactive elements within its rocky components, would have been sufficient to warm the interior to the point where the ices could soften and melt. In this warmer, more fluid state, gravity could begin its work of sorting the materials. The heavier, denser silicate rocks would have sunk towards the center, gradually accumulating to form a large, solid core. The lighter water ice, along with other frozen volatiles, would have risen to the top, forming a thick, planet-encircling mantle and crust. This process is fundamental to the evolution of any large planetary body, and the evidence that it occurred on Pluto is a clear sign that it has behaved like a true, complex world from its very beginning. The possibility of a subsurface ocean adds another layer of complexity to this internal picture. If it exists, this ocean of liquid water would be sandwiched between the solid, rocky core and the thick outer shell of water ice. It would be a hidden, dynamic layer in a world that appears, on its surface, to be entirely frozen. The existence of such an ocean is one of the most exciting possibilities in modern planetary science. And while its presence has not been definitively proven, the indirect evidence from the New Horizons mission has made it a very strong and compelling hypothesis. The surface of Pluto is a mosaic of different geological ages. While some areas, like the highlands, are ancient and heavily cratered, bearing the scars of billions of years of bombardment, other regions are remarkably youthful. The most prominent example of this youth is the western lobe of Tombaugh Regio, the vast nitrogen glacier known as Sputnik Planitia. Its complete lack of impact craters indicates that its surface is constantly being renewed, with the slow convection of the nitrogen ice erasing any blemishes on a geological timescale of just a few million years. This is astonishingly young for a surface in our solar system. It means that Pluto is not a dead, static world that recorded its history and then fell silent. Instead, it is a living, breathing geological entity with ongoing processes that are actively reshaping its face. This discovery has forced a complete rethinking of how small, icy worlds in the outer solar system can evolve. Previously, it was assumed that such small bodies would have lost their primordial heat long ago and would now be completely frozen and inactive. Pluto has shown us that this is not the case. It has found a way to hold on to a small but significant amount of internal energy, enough to power active geology and maintain a dynamic and evolving landscape. The polygonal, or cellular, patterns that cover the surface of Sputnik Planitia are the key to understanding the mechanism of this renewal. These cells, which are typically between 16 and 40 kilometers, or 10 to 25 miles across, are the surface expression of the slow, convective overturning of the nitrogen ice. The ice at the bottom of the glacier is warmed by Pluto's faint internal heat, causing it to rise. When it reaches the surface, it spreads out, cools, and then sinks back down along the boundaries of the cells. This process is similar to what happens in a pot of boiling water, but on Pluto, it unfolds at a glacial pace, with a single overturn taking perhaps tens of thousands of years. The boundaries of these cells are often marked by darker material, thought to be impurities, that have been concentrated as the ice flows. In some places, these boundaries are also where the floating hills of water ice tend to congregate. These polygonal patterns are the fingerprints of a living glacier, the visible proof of the hidden heat that still churns within the heart of this distant dwarf planet. The journey of the New Horizons spacecraft was not just a scientific mission. It was a race against time. After its launch in 2006, the probe had a 9.5-year journey ahead of it. During that time, Pluto was steadily moving away from the Sun in its long, elliptical orbit. This meant that with each passing year, it was getting colder. Scientists were concerned that if the spacecraft arrived too late, Pluto's thin atmosphere might freeze and collapse onto the surface, robbing them of the chance to study its composition and dynamics. The spacecraft was designed to be as fast as possible to minimize this risk. As it turned out, New Horizons arrived while the atmosphere was still robust, allowing for a detailed study. The flyby itself was a moment of breathtaking precision. The spacecraft, traveling at a speed of nearly 50,000 kilometers per hour, had to navigate a precise trajectory through the Pluto system, threading a needle through the orbits of its 5 known moons. It came within a mere 12,500 kilometers, or 7,800 miles, of Pluto's surface, close enough to see features as small as a city park. During this brief encounter, all of its instruments worked flawlessly, gathering a massive amount of data that has forever changed our view of the outer solar system. The data gathered by New Horizons is a gift that will keep on giving for many years to come. The initial flyby provided a snapshot, a single, glorious moment in the life of Pluto. But by carefully analyzing the wealth of information contained within the images, spectra, and other measurements, scientists can continue to unravel the complex history and ongoing processes of this fascinating world. Every new discovery raises new questions, prompting further research and deeper analysis. The data is a public archive, available to scientists and enthusiasts around the world, ensuring that the legacy of this historic mission will continue to inspire and educate future generations. The official symbol for Pluto, a monogram that combines the letters P and L, is a clever and fitting tribute. It not only represents the first 2 letters of the dwarf planet's name, but also serves as a subtle homage to Percival Lowell, the visionary astronomer who first set the search in motion. This symbol, often used in astronomical charts and publications, is a compact piece of history, connecting the ancient art of mythology, the rigorous science of orbital mechanics, and the human story of discovery. Before its reclassification, Pluto held the distinction of being the smallest planet in our solar system. For decades, school children learned of the 9 planets, with Mercury as the smallest of the inner worlds, and Pluto as the tiny, icy outpost at the edge. Its small size was one of its defining and most well-known characteristics. The discovery of Charon in 1978 was the key to determining its true dimensions and mass, confirming just how diminutive it really was. While it has now lost its planetary title, its small stature remains a crucial part of its identity, a reminder that even the smallest worlds can harbor the biggest surprises. The reclassification of Pluto was not an isolated event, but the culmination of a paradigm shift in our understanding of the outer solar system. A major catalyst for this change was the discovery of other large bodies in the Kuiper Belt, none more significant than a world named Eris. Discovered in 2005 by a team of astronomers led by Mike Brown at the Palomar Observatory, Eris was initially announced as the 10th planet. Early measurements suggested it was even larger than Pluto, a discovery that threw the tidy 9-planet model of the solar system into disarray. If Pluto was a planet, then Eris, being larger, certainly had to be one too. This forced the astronomical community to confront the question of what a planet truly is. The subsequent debate led to the formal definition and Pluto's reclassification. Later, more precise measurements from the New Horizons flyby of Pluto and other observations of Eris revealed a more nuanced picture. While Pluto is slightly larger in diameter, Eris is about 27% more massive, meaning it is significantly denser. This tells us that Eris is composed of a much higher proportion of rock relative to ice compared to Pluto. Eris is, in essence, a rocky heavyweight, while Pluto is a larger but icier lightweight. The existence of Eris and other large Kuiper Belt objects like it was the proof that Pluto was not a solitary oddball, but the first discovered member of a vast and previously unknown population of icy worlds. Another key feature that distinguishes Pluto's place in the solar system is its peculiar and stable orbital relationship with the giant planet Neptune. The two worlds are locked in a 3-to-2 mean motion resonance. This means that for every 3 times Neptune completes its vast circuit around the Sun, Pluto completes exactly 2. This precise, repeating gravitational interaction acts like a celestial gear, synchronizing their paths through space. While Pluto's eccentric orbit does cross inside Neptune's, this resonance ensures that they are always in different parts of their orbits when this crossing occurs. Whenever Pluto is at perihelion, its closest point to the Sun and inside Neptune's path, Neptune is always at least 50 astronomical units, or about 7.5 billion kilometers, away. The resonance prevents them from ever having a close encounter, stabilizing Pluto's orbit over billions of years and protecting it from being flung out of the solar system by the gravitational influence of the much more massive Neptune. This resonant relationship is not unique to Pluto. Many other objects in the Kuiper belt share this same 3:2 resonance with Neptune. This group of objects, which follow a similar orbital path to Pluto, has been collectively named Plutinos, or little Plutos. They are a testament to the powerful influence of Neptune's gravity in sculpting the structure of the outer solar system. Early in the solar system's history, as Neptune migrated outward to its current position, its gravity would have swept through the primordial Kuiper belt, capturing objects like Pluto into these stable, resonant orbits, while ejecting many others. Pluto is therefore the king of the Plutinos, the largest and most prominent member of a vast family of objects that dance to the same gravitational rhythm. When we rank all the known objects that orbit our Sun by their sheer physical size, Pluto finds itself in a respectable, though not leading, position. It is the 10th largest known object directly orbiting the Sun. This list is, of course, dominated by the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, followed by the terrestrial planets, Earth, Venus, Mars, and Mercury. After these 8 planets comes Ganymede, Jupiter's massive moon, but it orbits a planet, not the Sun directly. So, in the list of primary bodies, Pluto is preceded by the 8 planets and its rival dwarf planet, Eris. This ranking places it firmly in the category of significant solar system bodies, a world large enough to have a complex geological history and a dynamic present. Following the triumphant success of the New Horizons flyby, the question of a return journey naturally arises. However, as of now, there are no approved or funded missions planned to go back to Pluto. The immense distances, the long travel times, and the high cost of such missions make them a rare undertaking. The New Horizons spacecraft itself was a product of decades of planning and advocacy. While scientists would love to have an orbiter to study Pluto's long-term seasonal changes, or a lander to analyze the composition of its surface ices directly, such a mission is likely many decades away. For the foreseeable future, our understanding of this distant world will continue to be shaped by the precious data gathered during those few fleeting hours in 2015. The New Horizons spacecraft did not stop after its encounter with Pluto. Its journey was only just beginning a new chapter. With its primary mission accomplished, the spacecraft used a gravitational assist from Pluto to alter its trajectory and continue deeper into the Kuiper belt. Its new destination was a small, ancient object known as Arrokoth, a primordial worldlet that has remained largely unchanged since the dawn of the solar system. The successful flyby of Arrokoth in 2019 provided the first close-up look at one of the fundamental building blocks of planets. Now, the spacecraft continues its epic journey, pushing ever farther into the darkness, a silent ambassador from Earth to the stars. It will continue to travel through the Kuiper Belt for years to come, and eventually, it will leave our solar system entirely, becoming an interstellar traveler, carrying a small sample of Clyde Tombaugh's ashes and a message from humanity into the vastness of the Milky Way galaxy. Within the diverse population of the Kuiper Belt, Pluto is a proud member of the group of objects known as Plutinos. This classification, based on its resonant orbit with Neptune, links it to hundreds of other known objects that share the same climactic dance. These Plutinos are a dynamically stable family, protected from Neptune's disruptive influence by the precise timing of their orbits. Studying this population helps scientists understand the early history of the solar system and the processes of planetary migration that shaped the architecture of the outer solar system. A prominent and enigmatic feature on Pluto's surface is a long, dark, whale-shaped region that stretches along its equator. Informally named Cthulhu Macula, after the cosmic entity from the horror stories of H.P. Lovecraft, this vast, reddish-brown terrain is one of the darkest areas on Pluto. It is thought to be a region where the surface is coated in a thick layer of tholins, the complex organic molecules created by the irradiation of methane. Its dark color means it absorbs more of the faint sunlight than the brighter, icy regions like Tombaugh Regio. This area is also much older and more heavily cratered, indicating that it has not been recently resurfaced by geological activity. Cthulhu Macula represents the ancient, primordial crust of Pluto, a landscape that has been exposed to the harsh radiation of space for billions of years. Pluto's thin but complex atmosphere exhibits variations with altitude. The temperature is not constant as you move upwards from the surface. In a surprising discovery, the New Horizons mission found that the upper layers of Pluto's atmosphere are significantly colder than had been predicted, at about minus 203 degrees Celsius, or minus 333 degrees Fahrenheit. The reasons for this are still being studied, but are likely related to the way gases like methane and carbon monoxide radiate heat away into space. This temperature profile has a major influence on the chemistry of the atmosphere, affecting how the haze layers form and how quickly the atmosphere escapes into space. Finally, despite its cultural significance and its status as a major solar system body, Pluto remains forever hidden from the unaided human eye. It is simply too small, too far away, and too dim to be seen from Earth without the help of a telescope. Even with a good amateur telescope, it appears as nothing more than a faint, star-like point of light. It took the dedicated search of Clyde Tombaugh, using a powerful, specialized instrument, to finally pinpoint this elusive world. This intrinsic invisibility is a fitting characteristic for a world named after the god of the unseen underworld, a remote and mysterious realm that only reveals its secrets to those who search for them with patience, ingenuity, and a relentless desire to see what lies beyond the edge of our vision. And so, this world remains a secret to the unaided eye, a faint and distant traveler, visible only to the patient and the well-equipped, just as it was for all of human history before a young man from Kansas patiently compared the darkness on 2 panes of glass. From that single, shifting point of light, a world has resolved itself into stunning clarity. We have seen its vast, beating heart of frozen nitrogen, stood at the foot of its mountains of water ice, and watched the sun filter through its delicate, blue haze. Its story forced us to look again at the familiar map of our own cosmic neighborhood and redraw the boundaries, not to diminish a world, but to better understand a new and crowded frontier it calls home. The journey to Pluto is a testament to the power of human curiosity, a story of how we chase ghosts in the data and pursue faint whispers from the dark. It taught us that a world does not need to be a planet to be profound, and that the most distant, frigid realms can harbor a dynamic, unexpected, and intricate beauty. It is a reminder that the universe is not required to conform to our simple classifications, and that its grandest secrets are often held by its quietest and most remote inhabitants. For every world we have seen, countless others remain as Pluto once was, a faint and distant possibility, waiting patiently in the dark for a curious eye to look its way.